Hi everyone. Today I'm gonna give you a very short summary on the contents that we're gonna cover in final exam. So as I told you, yeah, this is not a mandatory lecture that you have to listen. So I'll just download like about 30-minute video or less, summarizing the contents, and please listen to this video if you want. If not, yeah, just forget about it and just download the my summary lecture note and try to have the overview of the entire semester. Okay, it's really important to have the overall big picture on what you have learned during this semester. It's okay to forget the little tiny detail and equations. Okay, however, if you forgot the story and big picture, it means like you didn't learn anything, right? So yeah, please try to remember and keep the big picture in your mind. Okay, so so let me begin the summary lecture by giving you the big picture of ME231. As I told you, the main topic of this ME231 course is predict the maximum stress, so that by comparing this maximum stress with the allowable normal stress and allowable shear stress, yeah, you predict whether the structure is reliable or not. And regarding the second one is about predict the deformation and deflection. Okay, so these are like two main topics, and throughout chapter 1 through chapter 11, yeah, we discussed the how to achieve our goals, how to do topic 1 and topic 2 by considering mechanical equilibrium and some like a geometrical analysis, and considering material properties. Okay, so before midterm we covered more like a you know divide and conquer strategy only. Like we have a relatively simple loading mode, like only axial, only bending, or only torsion, and we learned the concept of normal stress and shear stress, and what kind of stress generated from what kind of force and torque. That's what we have done. Starting from final exam coverage content, yeah, we started to mix out like different loadings, NTVM, and try to combine the loadings and predict the maximum normal stress and maximum shear stress, and compare that with material property to predict the failure. And we also discussed about more circle concept to correctly obtain the maximum normal stress and maximum shear stress. That's what we have done after final midterm exam. Regarding the second topic, yeah, we didn't discuss about deflection after chapter 3 before midterm. However, after midterm, we discussed about so-called Euler Bernoulli beam theory, and in energy method chapter, we considered like a work energy method, and derived how to the way to obtain the deflection out of the strain energy calculations. So before begin, because chapter 5 has really close connection with chapter 6, let me give you a very brief introduction about chapter 5. In chapter 5, we defined like three types of loading, transverse loading and experiments, and we defined the sign convention for external loading. We also defined the sign convention for internal shear force V and moment M. Okay, so by keeping these sign convention as it is, then you can use the equations that we derived after this chapter in a consistent way, such as like a beam deflection. Okay, and then we also discussed about like three different supports whose boundary condition is expressed in like a different mathematical way. And then we also discussed about like the connections between point force and distributed loading to the distribution of shear force V and moment M. Okay, so these are what we have considered back in chapter 5. So in chapter 6, we finally started to consider shearing stress. Shearing stress is stress that is like parallel to the cross-sectional surface. Okay, and after analyzing the mechanical equilibria, we are able to derive simple BQ over IT equation. Even though the equation looks simple, the evaluation of this equation is relatively complex because regarding this Q will be the function of position Y, and so you have to perform this integration at each point where you want to obtain the shear stress. And regarding this thickness, you have to consider T should be function of Y. Okay, so shearing stress distribution is the most complex distribution that we can handle until now. Out of the N, B, Tm, out of those four reactions, the other stress expression is relatively simple, but this is the most complex expression for stress out of the force V. Okay, then what we have done is, after we discussed about shearing stress, we also considered like this hollow structure. Even though our force is vertical, like we just learned that we can have this longitudinal direction shearing force, and we also discussed about a strategy to obtain this longitudinal direction shear stress. Okay, so this is typical example problem where you take relatively symmetric this red zone. After obtaining the symmetric zone and found that top and bottom is stress free, by performing this Q integral, then you can obtain the shearing stress at this two side and longitudinal direction. Okay, so it's all about taking the correct red zone. Okay, so you take this red zone with like a maximum maximum fraction of the traction free stress free area, or you do better take the red zone with quite symmetric geometry. Then you can obtain the longitudinal shear stress using relatively simple expression. Okay, we also discussed about shearing stress in a symmetric thin-walled member. If you consider thin-walled member, because of the this relationship, tau xy and tau yx should be equal to each other. So whatever direction you are taking, whatever volume you are taking, because the both side is traction free, you cannot have a shearing stress component that is along this that direction. Okay, so it's impossible. So the only way to have shearing stress is along this thin-walled beam. Okay, so that's how we consider this thin-walled beam, thin-walled structure and the shearing stress distribution problems. And then we discussed about unsymmetric loading and shear center problem. So in handling unsymmetric loading, I told you that if you don't apply the vertical force in a correct position, you cannot apply this relationship. Okay, because it will induce a twist. Okay, so what we have done was we assume that this equation holds. After assuming that this equation holds, you can convert this to a statically equivalent problem, and from converting this problem into like a single vertical load problem, then you identify the location of shear center, and this is the position where if you push this shear center, you're not gonna have any twist, and because you don't have any twist, you can have this shearing stress equation. Okay, so this is really weird way of solving problem and really indirect way of approach the problem, but considering twist is out of the beyond the scope of this course, we'll just use this indirect method. Then in chapter 7, we discussed about Mohr circle. Mohr circle is nothing but a just memorization method way. Okay, so suppose that if you have a vector f, and depending on x y coordinate or x prime y prime coordinate, your component of f is different. Even though f is an identical entity, the reading of f is 4,3 for xy coordinate and 5,0 for x prime y prime coordinate. Okay, so and then we discuss about general vector transformation rule. We do something similar for stress. So the stress is a entity that is just a unique and existing entity at specific point. However, depending on xy coordinate, depending on x prime y prime coordinate, you're gonna have different component of stress. So after obtaining the component of stress from mechanical equilibrium consideration, you found that compared to vector transformation formula, this formula is much more difficult to memorize. So a easier like a graphical way of memorizing this formula is so-called the Mohr circle, and will be always important and useful to memorize how to use Mohr circle. And we also discussed about general stress state, and something we learned was that for any arbitrary stress state, we are guaranteed to have x prime y prime g prime coordinate such that there is no shearing stress component, and we call this coordinate system as principal axis, and we call the normal stress for that specific coordinate system as principal stress of the stress state. Okay, and we then discussed about Mohr circle in 3D, even though we didn't discuss how to correctly draw this thing, at least for plane stress problem, where we can identify at least a value of one principal stress. Then I told you a empirical way to construct Mohr circle in 3D. Then after obtaining the Mohr circle 3D after discussing about Mohr circle in 3D problem, we move on to the thin walled pressure vessel problem. The thing we have to remember about thin walled pressure vessel is that if we obtain the maximum normal stress or maximum shearing stress out of 2D Mohr circle, it does not correctly give the maximum normal and shear stress values. So our approach should be, we have to consider 3D Mohr circle, and after considering 3D Mohr circle, we can correctly obtain maximum shearing stress, and by comparing this maximum with allowable shear stress, you can determine whether the pressure vessel is strong or not. Then we also considered the Mohr circle for strain problem. So when considering the strain problem, something we have to be careful is the vertical axis indicate the value of gamma over 2, the shear strain over 2. Other than this, the expression for R and expression for X and Y is almost identical with this typical Mohr circle examples. Okay, so instead of tau, you plug in gamma over 2, and that will give you the way how to use the Mohr circle for strain. We then discussed about shear strain rosette. Strain rosette is the concept where we have a sensors for normal strain, and after measuring 3 normal strain constant and using the stress transformation formula, we can obtain shear stress out of 3 normal strain normal strain measurement. And then we discussed about relation between Mohr circle for stress and strain. Here, what I can tell you is that if you found like in principal axis out of Mohr circle for strain or out of Mohr circle for stress, the principal axis you have gotten should be identical and should be equal to each other. However, because of the Poisson ratio, even though you found that one principal stress turns out to be 0, it does not guarantee that corresponding principal strain is 0. Okay, because even though it's principal plane stress problem with one component of stress being 0, that component can be expanded or shrink due to the Poisson ratio. Okay, and the deformation of like x direction, y direction, z direction along the normal direction, they are coupled through the Poisson ratio. You cannot say that this guy. Okay, then we move on to a chapter 8, where we considered lots of complex problems. We first considered like pressure vessel with welding joint. Here, the only thing you have to consider is you only need to consider in-plane Mohr circle, because the welding joint gives you quite easy plane to crack. Okay, for crack to propagate, so that you don't need to worry about like any other plane other than the this welding joint. Okay, so if you found the word welding joint when solving some problem, don't worry about 3D Mohr circle, just to focus on in-plane Mohr circle. And then we discussed about like a beam and shift problem. Yeah, what we have learned is that typically, Mohr circle and principal axis and principal stress is not like a uniform over the entire location. Principal axis and principal stress, there will be function of position. Okay. Then we discuss about pressure vessel under various external loading. Here, if you don't find the wording about welding joint, if this pressure vessel made out of other processing, then you have to consider 3D Mohr circle to correctly obtain the maximum normal stress and maximum shearing stress and the plane with plane of failure. Okay. So this is chapter 8 contents. In chapter 9, we move back to the beam deflection problem and discussed about how to obtain deflection out of beam bending. Okay, so back in chapter 5 and chapter 4, we only discussed about distribution of moment and distribution of shear force, and that's it. We didn't discuss about the effect of those shear stress and shear force and bending moment distribution. Here, starting from the distribution of shearing stress and distribution of moment, we obtained the shape of the beam after deflection. Okay, so we made assumptions, small deflection assumption and high aspect ratio assumption. Under these two assumptions, we can say so-called Euler-Bernoulli beam theory. Okay, so actually these three lines are equivalent to each other due to the derivative and integral relations between W and V and M, and we also learned that this theory is valid only if L over D is larger than 10. Okay, so we also discussed about a step-by-step procedure to solve the problem, starting from statics and reactions, and then obtaining the moment distribution, then integrating this moment distribution twice to obtain y, and we found that after double integration we're gonna have two integration constant, and we can obtain the integration constant by utilizing the boundary condition. Okay, so the boundary conditions we can use are following, and even though we have relatively discontinuous distribution of force and moment, we can use the interface condition where the deflection of left side and right side should be equal to each other to have a continuum continuous the beam, and second condition is the derivative should be equal to each other. If this derivative is not equal to each other, it means that double derivative will be infinity. If double derivative is infinity, double derivative is connected through mx, and it means that moment is infinity, which is not physical. So you can also use this condition. Okay, so based on this condition and the boundary condition, we can obtain integration constant. We also discussed about like a quadruple integration method, but it's almost identical to double integration method. And interesting problem we considered was statically indeterminate problem, where we typically see this redundant support. Okay, due to this redundant support, we have like more unknowns than the available mechanical equilibrium equation. So of course you can solve this problem by doing double integration method, but you encounter a problem where we have to handle many unknowns with many coupled linear equations, which going to consume a lot of time without giving you so much intuition. Yeah, that you are guaranteed to solve this problem, right? If you have 5 independent linear equation, if you have 5 unknowns, that you can solve the solution, right? After that, I would say that's a simple labor. In Korean, it's just a nogada, right? But you don't know nothing, so you need more efficient methods to solve this problem. So as an alternative, I told you superposition method. Yeah, actually superposition method was suggested in chapter 2 and chapter 3 to handle statically indeterminate problem. So if you have like a known solution for easier problem, then you can obtain another equation out of this constraint on deflection. Then if you combine 3 equations and 3 unknowns, you can solve the problem, okay, without increasing the number of unknowns. Okay, so this is a alternative way of solving statically indeterminate problem. then we moved on to relatively recent energy method. So in energy method, we learn about the strain energy density out of normal stress and out of shear stress, and for axial loading and bending and torsion and this shear force, we obtained the expression for strain energy of the structure, and we also discussed about why high aspect ratio is important regarding the validity of Euler-Beam-Bernoulli theorem. And then we discussed about a work energy method where we consider work and strain energy equivalent, because due to the energy conservation principle, and out of this you can obtain the deflection due to this force P, or instead of doing that, if you perform this integration, you can also obtain deflection. Okay, that's what we have learned from work energy method chapter regarding single load. And we can do this same thing in not only for point to force, we can do same thing for point moment and point to torsion, but the variable will be angle theta and twist angle phi. And then we also applied this partial U, partial P method for solving deflection of this linked joint problem, and we are able to relatively simply obtain how much the B point will move on the force P. Okay. Then after we discussed about single loading problem, we discussed about multiple load problem. Yeah, here one thing you have to remember is regarding the multiple load, after doing careful evaluation, yeah, you found the Maxwell's reciprocal relationship, and you also found that regardless of number of loadings, n point force and m point moment and l point torsion, after obtaining the strain energy expression, each deflection along that force, the twist angle corresponding to that torque can be obtained from partial U and partial P, or partial U, partial M, or partial U, partial T. Okay, so this is something worth memorizing. Okay, then after we learn about the multiple load problem and Castigliano theorem, we discussed about a dummy force method. Suppose that you have this simple structure on the vertical force, but the problem can ask what will be the deflection along horizontal direction. So here the method we have used was we assumed a dummy force along the horizontal direction, then write down the strain energy in terms of P and Q. So if you do partial U, partial Q, it will be deflection along vertical. If you do partial U, partial Q, it will be deflection along this positive x direction. After evaluating YB and YXB at Q equals 0 point, you can obtain the solution for original problem, which is deflection along horizontal direction. Yeah. Then I also discussed about how to apply those energy method for statically indeterminate problem. So here, due to this redundant loading, you have 3 unknowns, but you can only have 2 mechanical equilibrium equation. So here, the way we use the energy method is that we write down the strain energy in terms of m square and 2ei, because m can be written as function of fa, and partial u and partial fa will give you deflection at the end. If you combine the deflection from only this loading problem, and if you combine the deflection of this uniform DC loading problem, then they should be summed up to be 0 to satisfy the deflection boundary condition for simple support. Okay, so this offers you a third method to approach the statically indeterminate problem. Okay, so with this I can make a very short summary of what I have covered after midterm exam, and I just want to wish you good luck on your final exam. What can I say? Yeah, I also went through the tough examination period back in high school and university years. I know that it's quite painful. It's like when you look at this concept really carefully, you're not gonna see that there is nothing very deep, right? It's like if you think about this, you can understand this, but regarding the midterm and final score, that will be determined by, making like a less number of mistake. It's not about, testing your, deep thinking. It's about within limited time, don't make mistake, and that will give you good grade. Okay, so I know that it's quite tough, tough to be in that kind of competition for quite a long time, but I don't know, like as a professor, and given like a limited time, that will be the only way to distinguish the grade between you. So yeah, what I can tell you is that, please, practice. Please practice so that you can, minimize the mistake, and you can minimize the error, and by minimizing the error and mistake, you're gonna get high score and good grade. Okay, so I know that it's really, bad way of learning something, but it's only for final exam and midterm exam period, and please bear that, tough period. And after final exam and after midterm, like as I told you, it's okay to forget all the equations. However, what I want to tell you is that as a student of, KAIST, and to have like a overall understanding and intuition, please try to memorize the big picture view, summarize it in one picture. This is the way I summarize the summarize ME231 contents, but I highly recommend you to make your own summary and your own visual diagram about entire semester, which gonna help you your career as an engineer even after graduating from KAIST, and like a professor or researcher, whatever role you're gonna have. Okay, it will really help you. Okay, so please try to remember and draw your own summary diagram and memorize this. Okay, yeah, so thanks for listening to my lecture. If you have taken my summarizing video until now, and good luck to your final exam.